Imagine this. You spent, weeks building out this beautifully constructed infrastructure stack.
Oh, yeah, we've all been there.
Right. You ran your plans, everything looked totally clean, and it deployed flawlessly in the dev environment. So you get the green light, you merge to main, and the moment it hits production, total catastrophe.
He's absolute panic.
Exactly. Alarms are triggering, Slack channels are just lighting up, and after like an hour of sweating, you isolate the culprit. And it wasn't some massive architectural failure.
It never is.
No, it was a single hard-coded dev-only value that somehow slipped through a variable definition and just brought the entire production environment to its knees.
Yeah, that tiny string of text is exactly why infrastructure testing is, well, it's no longer just a best practice. It's literally survival at this point.
It really is. And, it's why Terraform's 1.6 update basically completely rewrote the rules on how we validate code.
Which brings us to our mission today. We are going deep into the critical world of infrastructure as code testing, specifically focusing on Terraform. Right, because we want to help you figure out how to validate your infrastructure before it breaks production.
Exactly. And we're pulling our insights today from the official Terraform test framework documentation, the Terratest specifications, and some of the latest exam prep materials for the HashiCorp Terraform Associate 003 exam.
Yeah, the 003 update is a big deal. They heavily penalize anyone who still treats testing as an afterthought now. The whole overarching theme here, the concept we really need to grasp is trust but verify.
Trust but verify. I love that. So, okay, let's unpack this. We hear the phrase shift left constantly in DevOps, right? Like usually people explain it as just moving testing earlier in the timeline.
Right, like shift it to the left side of the project board.
Yeah, but for platform engineers who are, writing complex stateful infrastructure, shifting left isn't just about saving time. It's about shifting that computational validation to a local, isolated environment before we ever actually make an API call to AWS or Azure.
Exactly, because the cost of a bug in IAC is, it's exponential.
Oh, totally.
Yeah.
I mean, fixing a typo in a local module takes, 2 seconds?
2 seconds and $0. But that exact same typo executing against a production database, that costs downtime, huge revenue loss, and potentially your job.
Yeah, no pressure.
Eh.
Right. It's basically like running a car factory with 0 safety checks.
Oh, that's a great way to look at it.
Right. Everything looks totally fine on the assembly line,
Right.
and the doors are shiny, but then someone gets hurt on the highway because nobody checked the brakes.
Yeah. If we connect this to the bigger picture, think of aerospace engineering rather than just traditional software.
Okay, aerospace. How so?
Well, you don't build an entirely new jet engine, bolt it to an airplane, and just fly it to see if it works.
I really hope not.
Right. You start with computational fluid dynamics, just static mathematical models on a computer. Then you move to wind tunnel testing, where you simulate the environment. And then, only after all that, do you do a controlled test flight. Platform engineering has to follow that exact same progression now. Infrastructure is code. It has to be treated with the same rigorous testing standards.
So we need the static analysis, the wind tunnel, and the test flight.
Exactly, before we ever touch the production runway.
Okay, so let's start at the very foundational level of that progression, like stopping bad data from ever even entering the system.
The static models.
Right. For instance, if I'm writing a module that deploys an EC2 instance, and it requires an Amazon Machine Image ID, an AMI ID, I know every valid AMI ID has to start with the prefix AMI.
Yep, that's the AWS standard.
So if a developer accidentally pastes a volume ID starting with vol into my module, I really don't want Terraform to blindly accept it, build a whole plan, attempt to deploy it, and then fail 5 minutes later when AWS finally rejects the API call.
Which is exactly where variable validation blocks come into play. This is your first line of defense.
Okay, how do those work under the hood?
So inside your actual variable declaration, you define a validation block. And it takes 2 arguments, a condition and an error message.
Simple enough.
Yeah, and the condition just leverages Terraform's built-in functions, so things like starts with or, rejects matching, to evaluate whatever string gets inputted.
And the really crucial mechanism here is the timing, right? Like the HCL interpreter evaluates this validation block during the parsing phase.
Exactly during parsing.
So it doesn't need cloud provider credentials. It doesn't even need to refresh the state file. It just looks at the abstract syntax tree, checks the string against your rejects, and if it fails, it just halts.
Immediate halt. It throws your custom error message straight to the console. The defective part, using your analogy, never even enters the wind tunnel.
I love that. But Variable validation has a pretty strict limitation, though, doesn't
Yeah,
it?
it does. It's completely isolated.
Right, because it only has context for that specific string or number you passed in. It can't look at the broader reality of your cloud environment.
Exactly. It's totally blind to the outside world.
So I'm imagining a scenario where, like, someone inputs a perfectly formatted, syntactically valid certificate ID. Variable validations can pass it, right?
Yep, it matches the regex, so it passes.
But what if that certificate actually expired yesterday? Variable validation can't catch that because it's just doing string matching. You can't, actively query the AWS certificate manager to check the date.
Right, and that limitation is exactly where postconditions step in.
Ah, okay. So how do postconditions differ from variable validation?
Well, preconditions and postconditions actually live inside the lifecycle block of a resource or a data source. And unlike validation blocks, they evaluate during the Terraform plan or Terraform apply phases.
Oh, meaning they actually interact with the cloud provider and the state file.
Exactly. So in your certificate example, you could configure a data source to read that cert from AWS and then attach a postcondition to it.
And that postcondition would say something like, after reading this data, verify the expiration date is greater than 30 days from today.
You nailed it. And if it's not, Terraform halts right there before it even attempts to attach that expiring certificate to your live load balancer.
That is so powerful. But it does bring up a question. If I'm already validating my variables, why on earth do I need preconditions or postconditions? Isn't having both, like, overkill?
Not at all, because it's about the what and the WHY. Variable validation protects your module from bad inputs at parse time. It's a quick syntax check. Lifecycle blocks, preconditions, and postconditions protect your infrastructure from bad environmental realities at plan and apply time.
That makes total sense. And honestly, that distinction highlights a massive trap on the Associate 003 exam, doesn't it?
Oh, absolutely. The exam heavily targets the timing and the specific mechanisms of these features.
Yeah, the trick question usually looks something like this. Which native Terraform feature validates that a variable value meets a custom requirement? And the options will be like validation block, precondition, and postcondition.
And let me guess, everyone picks precondition.
Yes. Because the word precondition sounds incredibly tempting there. It sounds like you're checking a condition before you proceed.
But if you choose precondition, you fail the question.
Right. Because preconditions check the configuration of resources or data sources based on the broader state. But if the question specifically asks about validating a variable value based on a custom requirement, it is always the variable validation block.
Always. It's a classic exam trap.
Okay, so we've got our inputs locked down with validation. We have our state realities checked with lifecycle blocks. But checking individual parts doesn't really guarantee the whole machine actually works together.
No, it doesn't.
So we have to move from those mathematical models into the wind tunnel. And this brings us to the testing pyramid. I feel like a lot of engineers misunderstand what the basic Terraform commands are actually doing under the hood.
Oh, for sure. People often treat Terraform Validate and Terraform Plan as if that's their entire testing suite.
Right, but they aren't functional tests at all. Let's break down the mechanics. Terraform Validate does not check if your code will actually deploy.
No, it just parses the abstract syntax tree.
Right, it just makes sure you haven't referenced a variable that doesn't exist, or it checks your code against the provider's internal schema. It operates completely offline.
It's basically a spell checker.
Exactly, it's checking your spelling. And then you move to Terraform Plan, which is essentially a state reconciliation engine, right?
Yeah. It takes your desired configuration, compares it against the current state file and the live cloud environment, and calculates the delta.
So if validate is checking your spelling, plan is like reading the blueprint. But a plan is effectively hallucinating API acceptance.
Hallucinating is a great word for it.
Right, because it just assumes that if the syntax is valid, AWS or Azure is going to honor the request. It is completely blind to logical conflicts that only show up during execution.
Yeah, a classic example of this is IAM permissions.
Oh, yes.
Yeah.
Tell me about the IAM role issue.
So you can write a plan that creates an IAM role and then immediately attaches it to an EC2 instance. The plan will show up perfectly green, everything looks good.
But then you run the apply.
And it fails. Because cloud providers have eventual consistency delays. The instance fails to create because the IAM role just hasn't fully propagated across all the AWS regions yet.
And a simple plan cannot test for that reality.
Nope. Which is exactly why the introduction of the native Terraform test command in version 1.6 was such a monumental shift.
Oh man, version 1.6 really changed everything. HashiCorp basically brought unit and integration testing directly into the native tooling, right? Using a totally new file type.
Yeah, the .tf-test.hcl files.
Right. Here's where it gets really interesting. Because you aren't writing traditional HCL resources in these test files. You write run blocks.
Yeah, so the run block allows you to execute a specific module, pass in a dedicated set of variables just for that specific test, and you can even dictate whether Terraform should just run a plan or go all the way through an actual apply.
And then inside those run blocks, you define assert blocks.
Yes, the assert block is the absolute core validation engine here.
So how does the assert block work alongside the run block?
Basically, after the run block executes the module, the assert block evaluates whatever state was just created.
Okay, like what kind of evaluation?
Well, you define a condition, like asserting that the resulting S3 bucket name matches a very specific string, or that a specific tagging convention was applied properly to every single resource.
And if that condition evaluates to false?
The test runner flags it as a failure, halts, and outputs your custom error message.
Wow. But wait, I see a huge bottleneck here.
What's that?
If I have, say, 50 different test cases checking all this different conditional branching logic in my module running, a full apply for every single test case, spinning up and tearing down real AWS infrastructure 50 times, that's going to take an hour and cost real money.
Developers will absolutely not run tests if they take an hour.
Exactly. So how do we get around that?
That exact bottleneck is precisely what the mock provider block was engineered to solve. Honestly, it's arguably the most powerful feature of the entire 1.6 testing framework.
Okay, this mechanism is fascinating. So when you define a mock provider inside your test file, you are essentially commanding the Terraform CLI to intercept the gRPC calls, right? The calls that would normally go to the actual AWS or Google Cloud provider.
Exactly. Instead of reaching out to the live cloud API over the internet, the mock provider intercepts it and generates entirely fake, locally computed responses.
It just hallucinates a successful state file.
Yes. It matches the provider's schema perfectly, but it's totally fake.
Oh, wow. So if my module has a data source that looks up existing subnets in a VPC, the mock provider intercepts that request and just returns dummy subnet IDs.
Yep. And what's fascinating here is you can even use the override data block to force the mock provider to return very specific values.
Really? Like simulating edge cases.
Exactly. You simulate edge cases to see how your conditional logic reacts to weird inputs.
So I can run 50 complex architectural simulations on my laptop on an airplane with no Wi-Fi in like 3 seconds for $0.
It completely changes the game for unit testing. It is the ultimate expression of your wind tunnel metaphor, rapid high-velocity unit testing of your logic with zero friction.
Okay, but let me play devil's advocate for a second.
Go for it.
If I'm mocking the provider, I am entirely relying on HashiCorp's mock to behave exactly like AWS.
Right.
And anyone who has worked in cloud engineering knows that AWS has, well, weird undocumented API quirks.
Rate limits, weird network realities.
Right. A mock simply cannot simulate that.
Right.
My mock provider might tell me that a security group was successfully attached to a database, sure. But it cannot tell me if that security group actually allows HTTP traffic from my web tier. It just assumes the abstract rules are correct.
That is a very valid point.
So how do we test the actual physical reality of the infrastructure?
Yeah.
If Terraform just introduced this native testing, aren't these third-party tools going to become obsolete?
No, they won't. And that limitation you just described is exactly why native testing does not replace the heavy artillery. When you need to verify the functional reality of a deployment, when you actually need the test flight, you bring in external frameworks like Terratest.
Ah, okay. The sources do outline Terratest, and it's a Go-based framework, right?
Yeah.
Which means we are leaving HCL entirely.
Entirely. You are writing full software applications in Go to test your infrastructure.
That sounds intense. Why is that added complexity justified?
Because Terratest is designed for deep, deep integration testing. You write Go routines that utilize the Terraform.option struct. You basically point it at your Terraform directory, pass in variables, and Terratest physically runs Terraform init and Terraform apply against the live cloud provider.
So real resources are provisioned, no mocks.
Real resources. And once they exist, the Go code executes functional tests against them. Terratest has built-in modules that can, like, SSH directly into the newly created EC2 instances.
Wow, really?
Yeah. It can execute HTTP GT requests against your load balancer to actually verify it returns a 200 OK status.
Okay, that's incredible.
It can even attempt to open a database connection to literally prove the firewalls are passing traffic. You are interacting with the built environment to prove it functions exactly as the business requires.
And because you're writing in Go, I imagine you can leverage standard software testing patterns too.
Exactly. And a really crucial mechanism here is the defer Terraform, destroy command.
How does it work?
Well, by using Go's defer statement at the very beginning of your test, you guarantee that even if the HTTP assertions fail, or even if the test completely panics and crashes halfway through, the teardown process will still execute at the end.
Oh, that's huge. So you won't leave orphaned, expensive test infrastructure just burning money in your AWS account all weekend.
Exactly. It cleans up after itself no matter what.
Okay, so the whole strategy here is layered. You use native Terraform tests with provider mocking for those high-velocity local unit tests just to ensure your logic and loops work. Then, in your CI/CD pipeline, you use Terratist to deploy a real ephemeral environment, run functional traffic tests to prove the architecture breathes, and then immediately tear it down.
That layered approach mitigates both logical errors and functional misconfigurations.
But, and this raises an important question, there is a glaring blind spot in both of those methodologies, isn't there?
There is. Functional tests only verify if something works. They do not verify if something is safe.
Exactly. Which brings us to the final layer of the sources today, static security analysis using tools like Checkoff and TFSec.
Yeah, because a misconfigured environment can function perfectly.
Right. I mean, a database that's wide open to the public internet will easily pass a Terratist HTTP assertion.
Yeah.
Because the data flows exactly as requested. It works perfectly. It's just perfectly insecure.
Security misconfigurations are the existential threat in infrastructure as code. Imagine a developer debugging some complex network issue, and they temporarily set an S3 bucket to public access just to eliminate IAM permissions as the root cause.
We've all seen it happen.
Right. They fix the actual issue, but they forget to revert the bucket permissions, and they commit the code.
And native unit tests will pass.
Yep.
The mock provider doesn't care. The Terratist suite will pass because the application can obviously read the public bucket.
But if you merge that to production, you have a massive data breach on your hands.
So how do Checkoff and TFSec stop this?
They operate on a completely different paradigm. They are static analysis engines. They evaluate your raw HCL code before a plan or apply is ever even executed.
Okay, so they're looking at the code itself.
Yeah, they map your code to a generalized cloud resource model, and then they evaluate it against hundreds of built-in security policies and known vulnerabilities.
But they aren't just doing, like, a simple text search for the word public, right?
Oh no, it's way more advanced than that. They traverse the complex graph of your variables and modules.
What does that mean in practice?
It means they can trace a Boolean variable that gets passed from a root module all the way down through 3 nested child modules just to see if it eventually disables the block public's argument on an S3 bucket.
Oh, wow. So it follows the logic all the way down.
Exactly. And if the static analysis engine detects that violation, it immediately fails the CI/CD build pipeline and throws a critical vulnerability report.
So we are really shifting security left. We aren't waiting for some cloud security posture management tool to flag an open bucket in the live production environment 3 days after it was deployed.
No, we catch the vulnerability directly in the pull request.
Man, it really is an incredibly robust, multi-tiered defense system when you put it all together.
It has to be.
Yeah, I mean, we've traced this entire shift-left philosophy today from its conceptual roots all the way to its tactical execution. We started with that first line of defense, using variable validation blocks to strictly control inputs during parsing.
And utilizing preconditions and postconditions in the lifecycle block to verify the reality of the state.
Right. And we highlighted that massive exam trap for you guys, remembering that validation blocks handle custom variable constraints while preconditions handle state evaluations.
Don't get tripped up on that one.
Then we mapped out the testing pyramid, separating the syntax checks of Terraform Validate and the state reconciliation of Terraform Plan from actual, real functional testing.
And we saw how Terraform 1.6 totally transformed the landscape with .tftest.hcl files using those run and assert blocks.
Yes. Breaking down how provider mocking intercepts those API calls, which lets you run hundreds of complex simulations locally without spending a dime.
But we also acknowledge the limitations of mocking, which is why we need the heavy artillery. Terratest for executing those Go-based functional traffic assertions against live infrastructure.
And finally, static analysis engines like Checkoff and TFSec to traverse the logic and hunt for security vulnerabilities before the infrastructure even exists.
This layered architecture matters because platform engineering has fundamentally evolved.
It really has. I mean, the HashiCorp Associate 003 exam focuses so heavily on this because you are no longer just, racking servers in a basement.
Yeah.
You are writing the genetic code of your company's entire technical foundation.
It's a huge responsibility.
It is. Understanding this testing pyramid isn't just about passing a certification.
Right.
It's about being able to merge a massive architectural refactor at 4:00 p.m. on a Friday and actually sleeping soundly that night.
The dream.
Right. You can log off knowing your automated pipeline, parse the inputs, mock the logic, functionally verify the traffic routing, and mathematically proved you didn't accidentally expose a sensitive database to the public internet.
Yeah, the tooling has matured to a point where relying on manual verification is practically negligent now. The frameworks are just built right into the ecosystem.
Which leaves a really fascinating horizon to consider as these frameworks keep evolving. I mean, we've moved from relying on external scripts to native testing languages with mock capabilities, right? And static analysis tools are integrating deeper contextual awareness every day. So as infrastructure as code becomes increasingly standardized, it makes you wonder, are we approaching an inflection point where AI agents can just analyze our root modules, understand the underlying business intent, and autonomously generate their own .tftest.hcl files?
Oh, man. That is the logical conclusion of the shift left movement, isn't it? Automating not just the execution of the test, but the design of the test itself based on the parsed state graph.
Exactly. We might be nearing a reality where AI agents preemptively map out and test edge case failure scenarios before human engineers even realize those vulnerabilities exist in their architecture.
That's a wild thought.
But until those autonomous agents actually take over, we are the ones who have to write the assertions. Because a perfectly architected infrastructure stack is completely useless if you haven't mathematically proven it can survive contact with reality.
Couldn't agree more.
Keep testing your edge cases, keep validating your state, and we will catch you on the next deep dive.